Okay, on to question 2. Here we have an amplitude modulated AM signal, and we need to answer the following questions about graphing this. So we've got our signal here, and part A says draw the amplitude modulated signal in the frequency domain in the graph below. So frequency domain should tell you that we're going to have a bunch of sort of lines that just go at the frequency that the signal is at, and they should go up to the amplitude. So we need to keep in mind that our usual terms look like A, amplitude, sine or cosine of 2 pi ft, right? And so if we look at each of these terms, we've got an amplitude and a frequency, an amplitude and a frequency, amplitude and a frequency, amplitude and a frequency, and an amplitude and a frequency, right? So those are all of the lines that should end up on our graph here. So let's go ahead and draw those. We've got 14 with 4600, so 46,000 kilohertz. So we've got a line here at 46, and that should go up to 14. And that should be straight. I'm just bad at drawing. So that's up to 14 there. And then we've got 2 at 50,000. We've got 2 at 42,000. We've got 5 at 56,000. And we've got 5 at 36,000. So that's it for the first one. Again, it should just be spikes at each of these locations, and they should go up to the amplitude. They should be at the x-axis of the frequency, up to the y-axis of the amplitude. So that's part A. Part B, what is the bandwidth of the AM signal above? So bandwidth is max, F max minus F min. In this case, this is the equation we should use since we have the maximum frequency and we have the minimum frequency. So this is 56 kilohertz minus 36 kilohertz, and that is 20 kilohertz. We can also use, if we have it, bandwidth equals to F max of the modulated signal, right? So if we've got the information signal that we're modulating, then we can calculate bandwidth in that way as well. And then part C, the AM signal is now demodulated. Draw the original signal VMT in the frequency domain on the graph below. So here we need to think about, I'm going to go up to the top equation again, what the AM signal looks like. So VAMT is going to be VC of sine or cosine 2 pi FCT plus, and then we're going to have a VM over 2 sine 2 pi FC minus FM t plus VM over 2 sine of 2 pi FC plus FM t. And we're going to have that for every component. And so if we sort of look at what our signal looks like in the frequency domain, we can kind of see that this middle frequency here is our carrier frequency, and this is our VC, our amplitude of the carrier signal. And then we've got 2 sidebands for each of the original signal frequencies. So we've got FC plus FM1, FC minus FM1, and that's at VM1 over 2, and VM1 over 2 are the amplitudes. Sorry, I should have drawn. This should be down here, and then this should be on top of that bar, right? So that's what that should look like. And then this one should be VM2 over 2, and FC plus FM2, and FC minus FM2 with VM2 over 2. Right, so that's what our chart looks like here, and that's the frequencies that we'd have in the original equation. So if we have these, we can reconstruct the original signal, which is just going to be VM1 sine 2 pi of FM1 t VM2. So that's what we should end up with down here, is that our VT, our original signal, should be VM1 sine 2 pi FM1 t plus VM2 sine 2 pi FM2 t, right? So given that that's our equation, we can pull those values from the original graph. So our sort of lower frequency F1 that is 4 kilohertz off of the original signal. So we should have a bar at 4, and that's going up to, it was 2 here, so it's going to be multiplied by 2. So that should go up to 4 volts. So that's our FM1, and this is our VM1 here from the original signal. Let me draw that out, sorry, looking at the top here. And then our second one is we've got 46 as our FC, and our FC minus FM is 36, so it should be at 10 kilohertz. And that M value, VM2, was 5 volts, so we should be at 10 kilohertz, and we should be at 10 volts. So that's our VM2 and our FM2 there. That's all we need to do for that problem. That's it.